Okay, so we're gonna talk about batteries and capacitors. So last time in the previous material that we talked, we kind of moved from the idea of vectors, electric fields and forces to talk about potential energy and electric potential. This actually makes our life very easier. Now we can build circuits. They don't have to be in three-dimensional space anymore. We can build a circuit and we can find how much energy we need to move the charges. We can find how to store energy and stuff like that only by talking about voltages and energy. The main two formulas, as we said, we derived last time, the definition of voltage, delta V, the change of voltage when we move between 2 points, is minus the electric field multiplied by the displacement. So of course, if we want to generalize, we have to put it in three-dimensional, or we can write it as a vector equation. Let's write it as a vector equation. E dot delta R. ده تحول بقى. Okay. But we need a dot product between them. So it means that the voltage only change when we move in the direction or opposite to the direction of the electric field. So if we move with the field, moving with the field, the voltage decreases. Decreases, and of course moving opposite to the field, the voltage increase. Moving opposite to field, the voltage increase. Or if you want, you can say it in the other way around, that the electric field points from high voltage to low voltage. Now, the other formula that we need is the potential energy. So if we have a charge here, when we talk about voltage, we're only talking about the source, the plates themselves, what they cause in the vicinity of them. But if we have a charge and we move this charge between 2 points A and B, then there's energy change. The energy stored in the interaction between the charge and the electric field changes, and the change in the potential energy is equal to Q delta V. So positive charges, when they move from high voltage to low voltage, they lose energy, and that's their tendency. You put an object on its own, it actually loses the potential energy. يعني كيف أنا مثلا بمسك طابة وبفلتها من إيدي, as I leave it, it actually falls down. It decreases the potential energy. نفس الشيء للcharges. Well, that's the general rule in physics. But the difference هو إنه الcharges فينا positive charge وفينا negative charge. So positive charges move with the field, يعني from high to low voltage, and negative charges move the other way around. طيب. Now we need to build the circuits that we're talking about. We need a source of voltage. We need something that gives us a constant potential difference between the plates. We do that using chemistry. So that's what is a battery. So a battery is a device that has two terminals, two sides to it. One we call the negative terminal, and one we call the positive terminal, or P and N. Inside the battery, there are chemicals that they can interact with each other only if we allow. So these chemicals are not mixed together and they are already interacting. They only interact by exchanging electrons. So these particles only react by exchanging electrons. And when they exchange electrons, we force that the exchange of electrons go through the outer side. So we only allow the exchange of electrons when we close the circuits. Of course, electrons have to move from the negative pole to the positive pole. Now, this interaction has a constant electric potential, the constant voltage between them. So it's an oxidation reduction reaction. So we have two metals, one is losing, one is gaining electrons, and they are separated. Now, when we allow the electrons to go from one side to the other, the reaction has a preferred direction, and it kind of give us energy. It loses potential energy, and it give it to the outer circuit. So the positive terminal, or the P terminal, is at higher potential than the N terminal. So when we say that we have a battery of 1.5 volt or 4.5 volts, the lithium ion batteries, I think volts, right? This means that the potential difference across its terminals is 1.5 or 4.5 volts. This constant voltage difference, if the battery is ideal, it's constant, is called the electromotive force of the battery. And delta V is the higher voltage, Vp minus Vn. And when we are in a circuit or we're doing a problem, we have to pay attention when we write delta V, if we mean delta V as Vp minus Vn or Vn minus Vp. It depends on where I'm going from where to where. If I'm going from P to N, actually it would be Vn minus Vp. So if I'm going from N to P, it would be Vp minus Vn. Now, when we're deriving formulas later on, you're going to see we're going to always take absolute value of delta V. So because we would be relating magnitude to the scalar. So the potential difference is a scalar. It could be positive or negative. The magnitude has always to be positive. So I represent it. I take the absolute value in my equations. Now, to represent the battery in the circuit, we're going to represent it in this way. We a small dash to represent the N terminal, of course, then the wire connected to it, and a large dash to represent the positive terminal of the battery. Now, the other thing we need to remember and have as element of our circuits are wires. Wires are what we consider perfect conductors. We talked a little bit about that before. So in real life, there is nothing perfect. In a conductor, there's charges that are free to move. In a perfect conductor, these charges move for free. So there is nothing holding them back. So they don't lose energy as they move. You know from physics, إذا أنا مثلا جبت تليفون عم بدفشه على الطاولة بدفشه وبفلته بيوقف. الانرجي اللي أنا أعطيته إياها by my hand is lost as heat as it slides down the table. لو كان ما في friction مع التيبل at all, then the phone would keep moving with no stop. Inside the conductor, there is not friction exactly, of course. This is totally different because we're talking about elementary particles. These electrons, as they move, they might collide or kind of interact with the atoms inside the material, and they would lose some of the energy that they allow them to move. But if we're considering our conductor as perfect, then we say that this loss is negligible. And if we put this conductor inside a field, these charges that were free to move here, represented as stars, they start moving. Usually these are electrons. So electrons move out. They have a negative side here. And when the electrons move out from the other side, there would be excess protons on this side. So there would be a positive side here. So there would be an electric field generated. So there is the external field here, E external. And then there would be a new electric field that is opposite to external, that is the induced field. Now these charges keep moving around until the net field, the total field, E inside becomes zero. So when E inside becomes zero, now we reach equilibrium. Of course, the idea of equilibrium is based on resistive forces. لأنه لو ما عندنا resistive forces, actually things keep going back and forth all the time. مثل pendulum. إذا أنتم بتيجوا بتعملوا pendulum. Do I have something to do a pendulum with? Whatever this thing. Let me open a camera.
Good morning,
So
doctor.
إذا عندنا نحن جيت زحت هيدي هيك and I moved it this way تركتها. It stops. Eventually it goes back to zero. It goes back to equilibrium position. This means that we lost the energy. لأن الانرgy that I gave it with my hand when I moved it this way, it's lost. That's actually what is based inside the conductor. So inside the conductor, we reach equilibrium. It means that the charges stops to move, and that's when the force becomes zero. The net force becomes zero, and that's exactly in the pendulum. It stops where the tension cancels out with the weight. Here, the tension doesn't cancel out with the weight. So here is where it cancels out with the weight. So when the net electric field inside the thingy inside the conductor becomes zero. طيب نحن باش بدنا نحكي عن electric field voltage. Zero electric field means constant voltage. So if I take any 2 points inside the conductor A and B, these 2 points have to be at equipotential. So it means that VA is equal to VB, or the difference between VA and VB is zero. It doesn't matter what is the exact value of VA for VB. Actually, we have no definition of the absolute voltage. على طول بس نحكي عن voltage عم نحكي عن potential difference, not exact value. So it makes sense to talk about exact value. All I need to know is they are equal to each other, so the difference between them is zero. Now this brings us to the first device or electric device that we're going to talk about, is the parallel plate capacitor. This is the device that we used from the beginning to describe what is an electric field. So it's made of two metal plates. The properties of these two metal plates, we're considering them perfect metals. So we're putting them in the plane of the page, and so the charge move along them for free in the YZ plane, and they have an area A, equal areas, and they are separated by a distance d between them. So the capital A is the area. We're going to use A for points and for the area. I don't think that's a big deal. It's not confusing. Now, what I'm going to do with my plates, I'm going to take perfect wires and I'm going to connect them to the two terminals of the battery, to the two poles of the battery. One side is connected to the positive pole, and the other side is to the negative pole of the battery. And we have a switch here. So we allow the switch to go on. When we close the switch, we complete the circuit. Now, that's what we said. These wires are perfect conductors. So the voltage at point P is going to be the same as the voltage at point A. The voltage at point N is going to be the same as the voltage at point B. Now, it might take a little time for this to happen, but usually this in very short, in less than a second, this equilibrium would be reached. So the difference in voltage between the 2 points on the plates, A and B, VA minus VP, is the same as the difference in voltage across the terminals of the battery. And the voltage across the terminal of the battery is determined by the chemistry of the battery. So that's equal to the EMF of the battery. So A becomes at higher voltage than than B. Now, the plates, as we said, they are conductors. So if I take any other point inside the plate, inside the same plate, they are connected by a conductor. So the voltage at A and at A prime, they have to be equal. There is no change in voltage when I move up or down or in and out of the plates. The only difference in voltage is when I move out of the plate. So I move along the X direction. So I move across the X direction, the voltage decrease. So now what I do is I want to find the electric field inside here, right? So as I move, I take 2 points. I take point A and B. I know the distance between them. So the displacement, if I move from A to B, is plus D, because I chose the x-axis from A to B. فيكم تختاروا x-axis بالعكس. But I'm moving from A to B, so the voltage is minus E, because this is equal to VB minus VA. As I said, I'm going the final minus the initial, so VB minus VA. So the voltage decrease as I move
دكتور
from
مش
A
عارف
to B.
إذا أنت قاصد بس حاطط الكاميرا.
نعم؟
مش عارف إذا أنت قاصد بس الكاميرا أون عندك.
You don't like face?
لا بالعكس يا عمي أكيد، بس بلكي أنت مش بالغلط.
لا it's okay, it's fine. مهم ما تكون عم تقطش، إذا ما عم تقطش عندكم that's fine. أنا عادة مطفي الكاميرا بس كرمال ما أصرف، يعني ما يكون الكونكشن مش منيح.
هذا اللي كان قصدي، ما مشكلة أكيد. عم أنت الباص، عمل اللي بدك إياه.
Thank you يا آدم. So now the electric field is minus delta V delta X. That's the electric field pointing from A to B. So that's equal to E over D, or the electromotive force over the displacement. So that's we already know. But what we know is now we know where it comes from. It comes from connecting these plates to the battery. And of course, we can see that if we move with the plates, there's no change in the voltage. So there is no electric field pointing in this direction or in the direction into the plane. Type. Now, what is the charge on the plates? To have an electric field, we need charge. When we turned on the switch, charges start moving. We have a full circuit, so charges can move. Now, originally, A كانت at low potential than P. So electrons move from A to P. Electrons move from low to high. So when electrons move in this direction, this is the electron moving, there will be extra positive charge here. And this positive charge spread out uniformly on the plate. Then here, the opposite happens on the other side. N is at lower electric field. So electrons move in this direction. So there would be extra negative charge here. Now, for the battery to be neutral, ليه؟ لأنه الباتري في chemical reaction بدها يصير بقلبها. ميلة بدها تاخذ electrons، ميلة بدها تخسر electrons، بس لازم يكونوا ضلوا neutral. Any chemical reaction has to be balanced, right? So number of electrons that move out of A are the same as the number of electrons that come to B. So QA is going to be positive, QB is going to be negative, but they have to be equal in magnitude. So QA is equal to minus QB equal to Q. Q, I'm taking it as the magnitude, as the positive number. Now, we know the relation between the electric field between the plates and the charge on the plates. The electric field between the plates, the double plate, it is 4 pi Ke sigma, or we can write it as sigma over epsilon 0. This is from the two plates. طبعا في عندنا electric field due to the first plate and the second plate, but they add up because they are in the same direction. So we got sigma over epsilon 0. طبعا sigma هي Q over A. So the magnitude of sigma is the magnitude of Q over the area of the plates. Now we can put that together. هلا E, the magnitude of E, we found it here. It's equal to delta V over D. We already know that. So we got this relation. Q is equal to epsilon 0 A over D times the voltage difference between the plates. The Q A will QB are scalars. They could be positive and negative. Delta V also is a scalar. It could be positive or negative. We know that the positive plate is going to be at higher voltage than the negative plate. So we know that VA is larger than VB. That we have to know. So this and this we have to know. Here, this relation, we're only talking about the magnitudes, so I'm going to take the absolute value of delta V. So this relation relates us to the magnitudes. This gives us the sign. We know that the electric field goes from the positive to the negative, and the voltage goes from high voltage to low voltage. So this actually gave us a very nice relation. It gave us the relation between the charge that I'm isolating on the plates. بعد التوتال تشارج تبع الديفايس كلها سوا زيرو. يعني انا اذا بطلع الديفايس من برا من بعيد بلاقيها زيرو تشارج. بس شو عم بعمل جواتها؟ عم بعمل ايسوليشن. بطلوا التشارجز ايكوالي ديستريبيوتد. صار في ميلي بوزيتيف اكثر من وميلي نيجاتيف اكثر من الثاني. So we have a separation of charge. And you know, charges don't like to be separated. When we separate charges, we are moving against the force. These four charges actually attract each other. We have a positive side or negative side. So there is a force on the positive side that is pushing toward B, and there is a force on B that is pushing toward A. So when we separated them, we moved against the force. يعني يمكن كأني أنا شو عملت؟ جبت طرمبة وطلعت مي على السطح. طلعتهم against the gravitational force. So I stored energy in them. So this device actually worked for storing energy as well inside the interaction between these two plates that they are charged. So let's put that together in simple form. So if we have a capacitor that has an area A and a separation D, we put a positive charge plus Q on one side and a negative charge minus Q on the other side. There would be a voltage difference between the plates. There would be an electric field. There would be voltage difference. The relation between Q and delta V is given by what we call the capacitance of the capacitor C. And C is only related to the shape of the capacitor, and it's equal to epsilon 0 A over D. Now, this is called the parallel plate capacitors because it's made of two plates that are equal area and they are parallel to each other. Now, we could have other forms of plate capacitors. We could have what we call the cylindrical capacitor اللي هو كيف الشريط تبع الأونتان. ما بعرف حدا شايف منكم شريط الأونتان بيكون في بقلبه بلاستيكي فيها شريط رفيع بالقلب وحول منه في شريط داير من دار. usually الجواني بيكون كبر البراني بيكون ألمنيوم. But this is the capacitor. So we have a cylinder inside and a cylinder outside. So this would be A and this would be B. This would have one charge and this would have another charge. And usually that's how they make their capacitors. And the parallel plate capacitor is very hard to manufacture as engineering. But of course, this we're going to have the capacitance only depend on the shape. It would have to depend on the inner radius, the outer radius, the length of the cylinder. We could have spherical cylinders, but of course spherical cylinders are harder even to make. بيكونوا طابة جوات طابة تاني. Now, the unit of capacitance, this quantity, we can relate it to Newton, and epsilon 0 is related to Newton, Coulomb, and meter squared, and then we have meter squared in the area with D. Or we can find it from this equation, it's Coulomb per volt, and that is usually called a farad. So 1 Coulomb per volt is called 1 farad. So now we said that this is device used to store energy. So we need to know how much energy is stored inside the capacitor. Now, when we were charging the capacitor, we moved electrons from plate A to plate B. إذا كان الvoltage between these two plates, delta V, no matter what I take, if I move them right here in the middle, or I move them through the wire from the outside, it doesn't matter. But as long as I'm moving from A to B, the change in energy for any charge is delta P is equal to Q delta V. That's the formula that we did at the beginning, right? بس المشكلة هون عندنا إنه دلتا في بحد ذاتها إذا برجع لهون دلتا في هي بتعتمد على الكيو. So delta V is not constant. As I'm charging the capacitor, even though it might be taking very انا لما حكيت هون حكيت دغري عن الاكوليبريوم قلت ال VA بتساوي ال VP وال VB بتساوي ال VN بس هاي الاكوليبريوم requires the charge to move from A to B. So I am charging the capacitor gradually. The first charge I move, the first amount of charge I move actually requires no energy because can the voltage A equal the voltage B? So the first of charge dq I move, the energy required, so I'm moving to a small charge, so I'm replacing delta by D. That's what I do in mathematics. It's equal to Q delta V, so it's 0. It requires no energy. Now, afterwards, each amount of charge I move, it has a certain voltage on it. I move Q, and I see what is the voltage at that moment. And then I move another dq, I see what is the voltage at that moment. Then I keep moving until I reach capital Q. When I reach capital Q, delta V reaches Q over C. So basically, the voltage increasing linearly as I'm charging the capacitor. So I take a small amount of charge and I see the voltage at that moment. I multiply dq by the voltage at that moment, and then I add it to the charge I'm doing. When I do that, it means that I'm looking at the area of this triangle here. So I'm integrating from 0 charge to capital Q of delta V dq. Now delta V is Q over C. Now the integral of Q dq is 1 over 2 Q square. Of course, بضل constant over C, and we have to take it from 0 to capital Q. So that is equal to 1 to Q square, the total charge that I put on the capacitor over C. Or I can write it as half Q delta V. So see how it differs from this formula here. This is Q delta V because the voltage is constant. Here we have half Q delta V. لأنه شقفة من الشارج كانت على low voltage, شقفة كانت على high voltage. Actually, it's kind of equally distributed. So we're kind of taking the average of it. Of course, if you don't, I don't want you to remember how to do integrals. This is just one integral we're going to use, and it's clear from the graphic, the method. We can take the area of a triangle. شو الاريا للتريانجل؟ هي height times base over 2. So the height هو Q over C, والbase هو Q. So we got half Q squared over C. So this is I'm not saying delta P anymore. I'm saying PE. So this is the energy stored, the total energy stored inside the capacitor, and I'm going to take it as a positive value. So I'm taking Q delta V. Now, this energy is stored inside, and then when we connect, if I take a wire and I connect those, the energy is going to be released out as we move along. So this is a review of all the equations that we did for the parallel plate capacitor. I'm going to turn off the camera. طيب. I'm going to discuss one new part اللي هو dielectric. هول البليتس اللي انا حاططهم قبل هون هن I'm assuming there is vacuum in between them. هلا في يكون vacuum في يكون air, but there's two problems that how I'm going to hold these plates at a constant separation D. If there is nothing in between them and they are attracting each other because I'm going to put positive charge on one and the negative charge on the other, then they're going to attract each other. One solution is to put some kind of an insulator material in between, like a paper or a piece of plastic or a piece of wood in between these two plates. That's the first problem. The other thing is, when we put this dielectric, it actually reduces the electric field that we have inside in the middle. Let's start with already charged plates. So أنا راح آخد plate عليه charge plus Q, plate عليه charge minus Q, and I'm gonna put the insulator between them. Now, the electric field, the capacitance without the dielectric, without this piece of material, is C0 equal to epsilon 0 A over D. The voltage difference is Q over C0, والاlectric field هي Q over C0 D, لأنه electric field, as we said, هي delta V over D. بس, even though this material is an insulator, but it is still made of charge. The material بعدها معمولة من atoms و molecules. والatoms وال molecules, they have positive charges and negative charges. So the positive charges are going to feel a force toward the negative plate, and the negative charges are going to feel a force toward the positive plate. So even though they cannot move, لو حاطط conductor أنا, كانوا هالcharges they move, وخلص بصير total charge zero. بينقلوا الالكترونز من ميل لميل. بس شو بيعملوا؟ ما they don't completely move. They orient in a way to reduce the force on them. يعني they swing or they kind of flip sideways ليصير negative side أقرب على positive side والpositive side أقرب على negative side. When they do that, they generate a new field inside. So we also have an induced field. بالconductor, induced field completely eliminate the real field. But inside the insulator, the induced field cannot completely eliminate. No, if it completely eliminates, بيرجعوا. So it has to have some value. So the net field, I want to, if I'm writing here a vector equation, I don't want to write negative sign. So the magnitude of the net field, here, let's write this as a magnitude equation. E net is equal to the original field that I put, E external or E 0, هي الإلكتريك فيلد لما يكون ما في dielectric minus E induced. So this is of the net electric field. So the induced electric field cannot be strong enough to bring E net to 0, but it reduces its magnitude. ليه؟ لأنه if it was going to bring it to 0, بصير عم نحكي عن conductor, ببطل insulator, right? So what happens is now we have a new field. This new field, E net, depend on E0, and it depend on what we call how strong a dielectric this material is. The word dielectric comes from this fact that this material can reorient, تاخد البوزيتيف لميلة والنيجاتيف لميلة. So I call this the dielectric constant. So the dielectric constant رح نعطيها السيمبل اللي هو مثل الكي، بس هو الجريك كي اللي هو كابا، اللي هو كي بس هيك شوي مزمومة إذا بدكم، بس بنسميها كابا. So كل ماتيريال حسب قد ايه هي بتقدر تبرم مع الفيلد بسهوله بيكون عندها larger dielectric constant. يعني مثل الاير، لانه الاير ما في actually كثير molecules anyways. So you see it's actually almost one. So it doesn't affect the electric field. يعني الاي نت تقريبا بتكون equal للاي 0. But when we go مثلا for paper, nylon, polystyrene, we have 3.7, 2.5, so a fairly value. But when you go to something like water, water is a very dielectric material. First, it's a liquid, it can reorient very easily. Second, oxygen is partially negative, hydrogen is partially positive. So you see it has a very large شو بسموه dielectric constant. وهيدي I don't know, starium titanate, it has a very large electric field. So now the voltage between the plates becomes equal to V0 over kappa. So we reduce the voltage. لما يكون كان الشارج ما فيه يتغير لانه it's an insulator. صحيح صحيح it's reducing the electric field, it's reorienting the charges in the middle, but they cannot transfer charge all the way. So the charge is fixed. So we have C equal to Q over delta, the new delta V. So I can say that this new C is equal to kappa C0. So by putting the dielectric, we increase the capacitance of the material. So now we can generalize. I don't know why I have C0 here. So C, again, another mistake to fix. So here the general formula for the capacitance became kappa epsilon 0 A over D. So we have to include the dielectric constant of this insulator that we are placing between the plates. Now, if you see in the table, we have another column in the table, which is called the dielectric strength. Dielectric strength هي basically إنه كل material قد ما كانت insulator إذا بحط عليها voltage كبير كتير تتحول لكوندكتور. And that's what happened in thunderstorms. In thunderstorms, air, which is an insulator, هي طبعا هي الفاليو when it's dry. لما تكون wet مثل thunderstorm يعني لما يكون في عندنا humidity, it changes significantly. But still, any material that is an insulator, if I put a large enough voltage, it changes to a conductor. how يعني الفورسز صحيح نحن قايلين انه how charges they orient themselves. بس اذا بحط الفورس كبير كتير, it actually breaks and it moves in different directions, so it becomes a conductor. So the dielectric strength is given in volt per meter. يعني كل متر من هالماتيريال قد ايه بده voltage ليتحول لكوندكتور. طبعا الwater, because it's a liquid, it's already a conductor. Vacuum cannot be changed to a conductor no matter how much voltage I put, because there is no charges to move in the first place. Air, each 1 meter of air requires 3 million volts, and it would change to a conductor. But that's for a meter. If you have a much smaller capacitor, usually capacitors are made with millimeters between them in electric circuits. So that would be much smaller. So if I put a capacitor to a 100 or 200 volts, it might change to a conductor. The other materials are in the same region, same order of magnitude تقريبا, all in the million volt per meter. Again, we're talking about per meter. إذا نحط ورقة أنا بين البليتس, الورقة الثيكنس تبع الورقة حتى مش بالمليمتر, right? It's micrometer, something like that. So let's solve this problem about this dielectric thing. A parallel plate capacitor with nothing between the plates has a 10 microfarad. It's connected to a battery. What is the charge on the plate? What is the energy stored in the capacitor? So I have أول شيء حاطه بدون شيء, and I connect it to the battery. The Q0 equal to C0 delta V. So it is 120 microcoulomb, or 120 times 10 power minus 6 coulombs. The energy هي Q delta V, half Q delta V. So it's equal to 600 times 10 power minus 6 joules, or 600 microjoule. Now, while the capacitor, while still connected to the battery, a slab of paper is inserted between the plates. So هول البليتس أنا مثبتهم بطريقة ما, وجبت ورقة وفوتها بيناتهم. شو بيصير بالانرجي؟ طيب الكابا للبيبر هي 3.7. I copied from the table before. هلا الكابا هون is unitless. So this dielectric constant is unitless because it's relating electric field to electric field. So Q is equal to C delta V. I have kappa C0 delta V. So kappa Q0. So the charge increases on the plates. So it means that the energy increases. So I'm storing more energy under the same battery. يعني على 12 volt battery, I'm increasing the energy that I can store inside the capacitor by putting the paper. Here لما يكون على طول, what we want to remember هو when the capacitor is still connected to the battery, the voltage is fixed by the chemistry of the battery. The charges can move for the voltage to stay the same as the voltage of the battery. But if I isolate the capacitor from the battery, the charges are stuck. Or if I isolated them from the battery or from any connection, they cannot move anymore. So the voltage might change, but the charge has to stay the same. That's the same question, but now we disconnect it from the battery. So قبل ما نحط الورقة, before we put the paper, we disconnected the capacitor from the battery. Now, because we disconnected, the charge has to stay the same. يعني the charge cannot change anymore. So now the voltage changes. لا لأنه الكاباسيتنس اتغير, الفولتج اتغير. يعني electric field بس حطيت لك الورقة أنا بده يقل. يعني الفولتج بده يقل. يعني الفولتج بيصير دلتا في 0 over kappa. So the potential energy becomes PE0 over kappa. So actually we reduce the energy that is stored in the capacitor. طب هالانرجي وين بتروح؟ Actually what happens is إذا هيدا البليتس هون, هيدا plus وهيدا minus. I bring the paper in. I put it here. Now هيدا البيبر بتبلش تعمل الاورينتيشن من هون قبل ما تفوت. بتصير هيدي ماينس وهيدي الميله تحت بلس. بصير في force pushing it in and the force pushing it this way. So how the forces up and down cancels out, but the net force بتصير in this direction. So we pull, الكاباسيتور بيسحب الورقه لجوا, and as it moves it keeps going faster and faster until the whole paper is inside. طبعا الورقه عم تمرق على حديده, it would lose some energy for friction and it would stop inside. لو ما في friction, it happens actually I would try to find a picture of it. It actually starts oscillating. بتصير تروح جوا او لبرا, بتصير تبرم in and out. So بصير في عندها kinetic energy مثل كأنها صارت oscillating مثل pendulum, تطلع وتنزل تطلع وتنزل until it stops in the middle as it loses its energy to friction. That's kind of neat, isn't it? يعني we're changing electric energy to motion now, kind of. So we're pulling the paper inside the plates. بس ما تنسوا ان احنا بنحكي عن very small charges here and very small energies. So say we're pulling in the paper, but here we're ignoring the mass of the paper, we're ignoring the weight of the paper, we're ignoring all friction forces. So it's very hard to see in real life because, again, these forces are, you're talking about energy of 10 power minus 6. So if you talk about the potential energy of the paper that has gravitational potential energy, it's going to be much larger than that. So again, this pull is only true if we can ignore all other forces on the material. طيب, I will stop here for two reasons. First, because we reached a good stopping point. Plus, I cannot talk anymore. ولا شجعني حنكي. I talk too much. Thank you for attending, to all 5 people who are here. May, how are you?
الحمد لله.
طيب, I will see you, Allah Rad, on Tuesday.
يعطيك العافية.
الله
Thank you,
يعافيك.
doctor.
Thank you, Karim, as well. Bye.